So we're happy to welcome Dr. Ramirez from UT. He actually must really like UT. He actually started out as a grad student at UT, and then took a couple of years as a postdoc at MPA, and then received a Cygni fellowship, which he actually split between Carnegie Observatories and UT. And yeah, now he's still there. So he's going to talk to us about the chemical composition of stellar twins, and yeah, so welcome.
Well, thank you, and thank you for the invitation, and thanks everyone for being here right now. So yeah, today I'm going to tell you about the research that we've been doing on using chemical abundances of stars to try to learn something about their planet populations, and also even a little bit about the actual process of planet and star formation. So I want to start with this artist rendition of how the process of star and planet formation might be happening. So we know planets form from a protoplanetary disk, and when this is happening, star is also forming at the same time. The star is not yet done. It's not in its final state. And you form planets, you can get things like this, which are big, giant type of planets, which probably have a rocky core, which is refractory rich, and they're surrounded by a very massive volatile rich envelope. And that composition is already different from the composition of the star. The star is a stellar composition. It's mostly hydrogen and helium. On the other hand, when you have a little planet, little planets are rocky. Terrestrial planets, Earth-like planets are rocky. They're refractory rich. And they might have thin atmospheres or surface oceans and things like that. But so the composition, the bulk composition of this object is also different from the composition of the star at the end. And it's also different from the composition of giant planets. So since all of this is happening at the same time, and the star is still accreting while these things are forming, so it is not unreasonable to ask the question of whether planet formation imprints some sort of signature on the final composition of the star. And so to illustrate our basic idea, the basic idea behind our work, I put this little cartoon here where you have a star, a very young star, and I've divided certain regions of the stars, which is the radiative core, there's the convective envelope, and then the disk from which planets form. And you have the star on this side and a twin of it, a star which is for all practical purposes identical to that other one. Now let's say that out of that protoplanetary disk, for some reason, in this star over here, planets form, but in this other one, planets don't form. If that's the case, now this protoplanetary disk, fraction of it, is going to end up in the star, because the star is still accreting while planets are forming. So if planets form, then only a small fraction of that is going to end up in the star. So I kind of represented that with this thin green layer over here. Now if that didn't happen in its twin, then all of that ends up in the star. Okay? Now, in this situation, if we are going to compare the surface composition of that star to its twin, there's going to be clearly a difference, even though they both started being identical. So this star is going to be deficient in chemical elements which are abundant in planets. So our basic idea, I mean, what we're looking for with the signatures of planet formation is this. We're looking for depletions of certain elements which we think are abundant in the planet. And of course, in order for us to see that, then there also have to be these other cases in which you don't have planets forming, and this would be just the star by itself. So in principle, this is possible. The problem is that planets are tiny, and then compared to the star as a whole. And then the signature is being imprinted on this convective envelope, which is also evolving as the star is very young. Right? So that adds a more complication to this story. And then in general, the problem is that the effect is going to be very small. If you try to calculate a typical Jupiter-sized planet, how much does it affect the composition of a convective envelope of a sun-like star when it's forming, it comes out to a number that is typically lower than 10% of change in composition of different elements. So that's kind of close to the limit of what we do normally in chemical abundance work. But we have a trick that we can use to go beyond that. So I'm going to tell you that in a moment. And so since we need this comparison stars, a twin of a star, our natural starting point is, of course, to use the sun. Right? So we try to investigate the sun. Also, the other reason we use the sun is because we know the sun has planets, both rocky and giant planets. So it's a good starting point. So there's been a couple of entire workshops devoted to the topic of solar analogs, stars which look like the sun for a number of reasons. We're interested in the sun. It's always a good reference for observations of many different kinds. Having a star that looks exactly like the sun out there in the night sky is good because the sun is during the day, right? You can't observe the sun at night, but so it's good to have twins as references. There's the question of how does the sun fare in the overall scheme of stars, populations, habitability, and also this kind of a silly question, but is the sun a solar type star? Is it normal in the context of G-type stars in general in the solar neighborhood? So there's a number of reasons why we would be interested in studying these types of stars. The reason we are particularly interested in them is because they allow us to get extremely precise chemical abundances and also stellar parameters. But in order for us to understand that, let me tell you about how we get, what dominates errors when we measure chemical abundances. So we go up to a telescope, we get a high resolution spectrum, a good one hopefully, right? And that eventually turns into stellar parameters and abundances. Right in the middle of that, there's this magic thing called physics. That's where all the heavy work goes into interpreting those the spectra of stars to figure out physical parameters and the chemical compositions of stars. So physics here is key. Problem is that when we're deriving abundances and say we have the sun on the one hand and we have a red giant, right? The physics of these two things are very different. Right? So when we're making a comparison of parameters or abundances or any other parameters, stellar parameters, that comparison is going to be dominated by systematic errors because this thing, physics here, it's always going to have some sort of uncertainty from our limitations in the modeling, but the limitations are going to be very different here than here. Situation is different when the two stars are the same. Because if you have two stars which are the same, they don't need to be solar twins. They can be just twins of each other. Even if the physics is incomplete, not fully known, if we do a direct comparison of the two, strict differential comparison of the two, all of those limitations, all of those problems with the physics, all of those systematic errors essentially cancel out. And so in this kind of situation, the error bars that you derive for the comparison of the two, whether you're deriving parameters or abundances, those errors are dominated by observational modes. So if you can find pairs of stars which are very similar to each other and you just compare them to each other, the error bar can become as small as big the telescope you can use. So you just just get better signal-to-noise data for your spectra, for example, and then you can keep reducing the size of the error bars. So we have found that that is in fact the case. So the trick is, again, that this chemical analysis of stars is dominated by uncertainties in the modeling. But if the two stars are the same, those uncertainties are the same, you do everything differentially, you're just comparing star A to star B, all these systematic errors, you don't have to worry about them anymore. Now, going back a little bit to the standard way we do chemical analysis. This is a classic plot of those of us who work on stellar abundances. This shows a large number of stars in the solar neighborhood. And this axis here is the oxygen to iron abundance ratio in this classical standard bracket notation. That means it's relative to the sun and on a logarithmic scale. And then on this axis is the iron abundance or the metallicity. So this kind of shows the evolution of the oxygen to abundance ratio for stars in the solar neighborhood. Different colors here represent different populations that exist in the solar neighborhood. So we have the thin disk over here, we have the thick disk in black, and then the halo is subdivided into blue and red. And without going into the details, because that's not the main topic of this presentation, the point is that this kind of investigations, which are what we normally do in the standard chemical analysis, we only need to have an error bar of about 0.05 dex. And the dex is because it's logarithmic, which comes to about 10% in either one of these quantities, Fe/H or the oxygen to iron abundance ratio. And here are those error bars close to this limit over here. Because you can see already, you can separate these different populations with this kind of precision. You don't need more to get to identify these different local populations and then try to figure out how you get this kind of distribution using galaxy models and whatnot, chemical evolution models. Now, you can normally do this for different types of stars. You can compare them to the sun. They don't need to be solar twins, and then you get that kind of error bar. And with good spectra, but not extremely high quality data, just good spectra, you can do this kind of work. When we work with solar twins, we can get this error bar down to the 0.01 dex level, which is about 2%. Now, why would you want to do that if you already can figure out things about the galactic chemical evolution with this kind of precision? It's because there might be something else hiding behind it. So that's what we're after. So we care about getting smaller error bars. Now, some might be interested in knowing what is a solar twin, right? What is the definition of a solar twin? And so one could say that a solar twin is a star that is identical to the sun. And from a more practical point of view, perhaps you can say that it's a star which has a spectrum that is identical to the sun. So here's a sample of 11 stars. And there's the sun here, observed on 2 different nights. The sun here is an asteroid, so it's just reflected sunlight. So it's observed at night with the same instrument and everything in the exact same configuration. And you can see by eye there is really no difference between any of those spectra over here. Once you start to look into the details, though, you will eventually find a difference. And even the most similar spectrum to the sun, you just need to get a better quality data, and then you're eventually going to find some difference. So trying to define a solar twin as a star which is identical to the sun is really not very useful in any way, for us at least. And so we eventually gave up trying to define what a solar twin is, and we just came up with a practical definition, with a pragmatic definition, which is that if a star is similar enough to our sun so that we can get to this kind of precision because of this systematics going away, then we call that thing a solar twin. Right? So just similar enough. It doesn't have to be identical. Just similar enough that we can do high precision stellar parameters and high precision chemical abundances. So if we can get down to 0.01 dex in the abundance ratios, then we call that a solid term. And this is what it ends up being in terms of stellar parameters. It's about 100 degrees plus minus from the solar temperature, 0.1 from the log of the surface gravity, and 0.1 from the iron abundance. So if the star has parameters within those ranges, then we can get this kind of precision, provided we get very high signal-to-noise data, again, because these errors, not these errors, but the errors in the parameters that we derive, again, are dominated by observational noise. So we need to get extremely high signal-to-noise for objects which are very similar to the sun, which might seem kind of an overkill, but as you'll see in a moment, what we find from that is very interesting. So in the spectra of the stars, most of these lines here are due to iron, and the majority of them are neutral iron. A few of them are going to be singly ionized. So you have iron 1 neutral and iron 2 ionized iron lines. And the way we use them to derive parameters is illustrated in this slide. So each point here, each of these blue crosses is an iron 1 line. We measure the iron abundance for each one of them. And each of the circles is an iron 2 line. We measure an iron abundance for each of them, starting with some assumption of what the stellar parameters are. So we start with this set of parameters for this star in particular, 18 Scorpion. And remember, this is always relative to the sun. So we're using differential analysis line by line, therefore removing all these systematic errors. So as you can see from this diagram here, this is the excitation potential of the lines. This is the reduced equivalent width, line strength, basically. Of course, what you want to get, if everything is good, you don't want to have correlations like this, because all iron lines should give you the same abundance within error bar. And also, iron 1 and iron 2 should give you the same average abundance, because they are both iron. So, so there's something not working good there. And of course, that's because the assumption might be wrong. So those parameters are not the correct ones. If you change them, and there are very different ways in which you can do that, essentially, in the end, you can achieve a perfect, what we call spectroscopic equilibrium. So the correlations disappear, the iron 1 and iron 2 lines give you the same abundance and all that. So you get consistent iron abundance from all the lines. Or statistically from all the lines. And these parameters that you get there are the parameters that you're going to assume are the parameters for the star. So here is the final result for this star, 18 Scorpio, and I should say this is our best case ever. For other stars we can do kind of close to this good, but not as good. This is our best example. And the reason I show 18 Scorpion being the best is because it's bright. It's one of our brightest, probably the brightest solar system out there. So we can get extremely high signal-to-noise for this one. Signal-to-noise here is 500. Now, typically, you would be happy with 100 of signal-to-noise, and very happy with a 100 signal-to-noise to do chemical abundance work. And for a solar type of star, if you're interested in doing galactic chemical evolution studies, 100 is enough, right? So we need to get to 500 because, again, we're limited by the noise entirely, right? Our error bars is just observational noise, so why not? Why not go to extreme high signal noise and get a better result? And this is, of course, very high spectral resolution. This is from Magellan, the Mike spectrum. So when we do this trick of, getting consistent iron abundances and whatnot, we get this result. Right? So that's the temperature, surface gravity log. And if you reach, that's not a typo. That's the error bar that you get from this kind of work. And that's the error bar that you get for FU/H. And once we derive the abundances of other elements, since the errors in the abundances of other elements are essentially come from these errors here that just propagate in the analysis. So those errors are also going to come similar to this number. So they're ridiculously small. Now, do we really think that we know the temperature with this kind of precision, 3 degrees, or this 0.003, which is, I think this is 0.5% or something like that? I'm not sure. I'm not sure, but these error bars, what they really represent is, when we do this trick of removing the trends with expectation potential, that we basically just changing the effective temperature of the star, and that changes that slope. Not only that, I mean, it's a whole game of 4 parameters changing everything simultaneously. But what these error bars mean is that this is how much you are allowed to change them, and you still get consistent abundances, mathematically consistent abundances. So if the physics behind all this is correct, then these are the true error bars. But that's a very big if, right, if the physics is correct. So now I have other reasons to really believe that these error bars are, if not real, pretty close to the actual error bars that we're getting for our
Have
stars.
you carried the covariance through on this? Because in the past, the problem with solar analog stars is there's covariance between these parameters when you're fitting. And so just looking at error bars is not necessarily what you have to do in order to figure out what the error is.
Right, it is all, there's a whole covariance matrix, and there's a couple papers that explain that, and we have replicated that in this work. So yes, you're completely right.
Just a curiosity, how long did it take you to do that signal to noise ratio in Magellan?
This is a bright star. It's a five and a half, I think. So this is probably 45 minutes or so. It's not terribly long. But for most solar twins, which are the ones that we work with, which are 8, 9 magnitude, we need 2-3 hours something like that on each star. Yeah.
Is the uncertainty here related to the scattering of the timelines and the plot?
The scatter is included.
But it's not derived from that.
It's not derived from that. No, it is like you mentioned before. It's from the covariance matrix of how you solve, how you get from here to here, right? So just going very quickly, when you see a trend that goes up, that usually means the temperature is too high. Oh, sorry, too low. So you need to increase the temperature, and so there's a derivative of the temperature with respect to, sorry, derivative of the slope with respect to temperature, which goes into, that's one of the variables in the covariance matrix that then goes into this whole error calculation. So, if we can get parameters and abundances with that kind of precision, now the question is, what should we expect for the abundances of all the elements, not just iron, and in particular for the abundance ratios, right, relative to iron, because iron can be different within 0.1 less for solar twins in our practical definition. And I have added this other word here. The spectra is nearly indistinguishable. It's not indistinguishable because otherwise, again, that is not a helpful definition. This one would be. So when you see this kind of plot, and before the work that we did, starting in 2008, 2009, perhaps the expectation was that when we looked at the abundance ratios of these stars, since they're all stars in the disk, thin disk stars, they all similar ages to the sun, and so we would have expected them to have abundance ratios very similar to solar, even at the 0.01 next level. And this is work from Melendez, Asplund, Gustafsson, and Young in 2009, which started this whole story. Now this is a plot that shows those 11 stars in the previous plot that have spectra that look about the same. And here are abundance ratios, X is any element, relative to iron, in the sun minus the star. And this is a function of atomic number. So it's about 20 elements here for each panel is a different star. Right? And this blue line shows 0, which would be solar composition. Right? So if our expectation was correct, the expectation that the abundance ratio should be solar, then all these points should be around the blue line with a scatter of about 0.01 dex, which is clearly not the case here. There's a much larger scatter, in some cases going all the way to 0.15 or 0.2 dex. On average, there is a scatter of about 0.1 dex. So that expectation was not correct, even though these objects have about the same temperature, the same gravity, the same iron abundance roughly than the sun. The abundance ratios of all these other elements are actually not solar at this level of precision. Of course, if we were still working with low signal to noise of 100, we wouldn't even worry about this scatter. That would be the expected scatter from just the observation of the noise. But we know that here the error bar is actually small, so this is true, real scatter. And what's more interesting is that this scatter is not completely random from element to element, from star to star, because if you take the average of those 11 stars, they don't center around solar. Some species, like carbon, nitrogen, and oxygen, are all the way up here, and it's statistically significant. And others, like barium, yttrium, zirconium, are down here, also statistically significant, different from the sun. So it's not a scatter, all evenly distributed around solar. There's actually something funny about the solar composition. So the weird star here is the sun. Right? The solar twins, on average, they're more or less consistent with each other. It is the sun that has a weird composition. It has a peculiar composition. So we call this plot is a signature that the sun has a peculiar composition when we compare it to its twins. And once again, this is atomic number, and this is just the average of those abundance ratios of all these different elements. Once again, before we didn't see this because we were working with this kind of error bars. That's consistent with this error bar. That's the scatter that you would expect just from observational noise. But if you have this kind of error bar, then you believe that this is real.
Sorry, just a quick clarification. The error bars on the data points here, what exactly do they represent?
In this case, is a combination of the error in the average of those 11 stars plus the error in the abundances themselves from each star.
So it's not just the scatter.
It's not just the scatter from star to star. It also includes the error bar from the abundances themselves from each star. However, the star to star scatter dominates a little bit. Not a lot, but it's larger than this error bar. Okay, so the solar composition then is peculiar. You see kind of a correlation here with atomic number. Aluminum doesn't fit though, and these other two don't fit very well either. To make the story short, what we found eventually is that the parameter that is driving these differences is the condensation temperature of the elements. So if the condensation temperature is here on this axis, and this is the same average difference between the sun and the solar twins, we see this very, very strong correlation that goes down like that. And again, you couldn't see it before because the error bar was too big. If you make a fit like this, is a broken line, then the sigma, which is the 1 sigma scatter element to element, would be about 0.01 dex, which is the error that we expected. So everything seems to be observationally very, very sound, even this correlation. And by the way, I would keep calling elements over here as is the norm. Volatiles, the elements with low condensation temperature, and refractories, elements with high condensation temperature. So this is, again, another way of showing what's the peculiar solar composition, that the condensation temperature is the parameter driving that peculiarity. And there's many ways of interpreting this. Yes, you have a question?
What's the condensation temperature?
This is 50% condensation temperature, is the temperature at which 50% of a given element condenses into something in a solar composition gas. So, because it depends on what's the composition and what's the temperature of what are the conditions of the early solar nebula. Now, it is a very useful quantity to differentiate elements which, as we're going to see in a moment, are more abundant in different types of planets. Let's just put it that way. It's practical for us. So there's many ways of interpreting this graph, I mean, this plot, and to kind of interpret what is the peculiarity. I'm going to say just one of the interpretations is that you can assume that the abundance of the volatiles are normal in the sun. And maybe I should step back a little bit. So this plot here is showing us abundances of elements relative to iron. Okay, we use iron because iron has a large number of lines. We can get the most precise iron, the most precise abundance for iron just because it's many lines. But it doesn't have to be iron. It could be any other element here as a reference. Right? It doesn't have to be Fe. So let's make an assumption for a moment that the 0 point, instead of being here, which is the case if you use iron as a reference, and if iron would be the normal thing amongst all stars, including the sun. Now let's make the assumption that the volatile abundance of the sun is normal, meaning that it is the same as in the other solar plates. If you make that assumption, then this would be the 0 point. Right? So instead of having x over Fe, you could have x over C, x over carbon, or x over oxygen, or something like that. Right? You pick one of these, or maybe the average of the volatiles, or something like that. Then the 0 is not here anymore; it would be up there. In that situation, the conclusion from this observational result is that the sun is deficient in refractory elements by an amount which is about 20%, which translated into mass comes up to about 4 Earth masses, which is a very interesting number because that's the mass, approximately, the mass of all the terrestrial planets plus the asteroids combined in the solar system. Now, to be fair, you can also say, well, what if it is the refractors instead, which is normal in the sun? If you make that assumption, then you have to say that the sun is enriched in volatiles instead. Right? That is a perfectly valid result also from this observational result. But if I tell you that, then I'll have to stop the talk because I won't have anything else to say. But just keep in mind that there's this other possibility. So we have to make this assumption to keep going with our idea. Oh, okay. So before I keep going with the interpretation, I want to say how I got involved with this project in the first place. I was not. If you notice, my name is nowhere there in this list of authors. When I finished at UT grad school, I moved to MPA to work with Martin Asplund, which was one of the authors of that other paper. And he came to one of our meetings with that plot, an early version of that plot. And I had worked for 5 years on things like non-LTE effects in stellar atmospheres, things like surface convection in stars, which all cause problems when it comes to deriving abundances. So my natural reaction was, I don't believe this. There's no way you can get chemical abundances with 0.01x precision. So I spent essentially those 2 years at Max Planck trying to prove them wrong. And the result of that was actually 2 papers which strengthened that conclusion. Like, I couldn't find a way that you can produce these trends with any sort of systematic error, residual systematic error that you can imagine. So I took different data sets. This is a different data set. This is a literature compilation, the worst thing you can do in this kind of work. I tried different model atmospheres. I tried combining spectra from different sources, all sorts of tests that we made to try to demonstrate that there was something, non-physical behind this result, and I couldn't find anything. So this is a very, very solid observational result. The interpretation of it is still debatable, but the observation is very, very, very solid. The sun is weird. The composition of the sun is weird. Now, we think that this is because that this deficiency of refractories in the sun comes from the formation of terrestrial planets, specifically terrestrial planets. And this is a paper from John Chambers in 2010 in which he proved that idea, which we wrote in our early papers, which is that what you have here is, again, this X, meaning any element relative to iron, as a function of condensation temperature. The solid line is the fit to our data. Okay? That's the fit to our data, and this the dots are what Chambers calculated what would happen to the sun if you take Earth, Mars, the other terrestrial planets, take all the asteroids and send them into the solar envelope, convective envelope. Mix it up, what would happen to the composition of the sun? Right? That's what you end up with, this black dots in that case, so the augmented sun. So if you do that, what this is basically telling us is that if you do that, if you send the Earth, the asteroids, and other solar system rocks back into the sun, then the sun would have a normal composition. Normal meaning the same as what the majority of solar twins are doing. The same as what the composition of the majority of solar twins are doing. So the hypothesis is then that this deficiency of rock that we see in the solar photosphere, and therefore in the solar convective envelope, is because those elements were retained. Like the planets took them away. Right? Instead of ending up in the sun, those elements stayed in the planets of the solar system. Now there's a number of issues with this interpretation, which I'm going to come back in a second, but let's say that that's true. Let's say that this hypothesis is correct. If that's true, then this opens up a very exciting possibility, which is that you can identify rocky planet hosts just by looking at the composition of the star. You don't need to do radial velocity, transit. I mean, you might want to do that to have more information. But if you just want to identify a very good candidate, all you have to do is look for stars which have a pattern that looks identical to the solar one at very high precision, of course. So here's an example of two stars, 18 Scorpio, one of the solar twins I showed you before, and here's another one in the black solid circles. So most solar twins show this trend with the condensation temperature. Right? And once again, that's the abundance of element, in this case relative to the average of carbon and oxygen. So most solar twins show this trend, but if you find a star which has a composition that is identical to the solar one, then that star should also be deficient in refractories. It should also show this deficiency of elements which are potential, that could potentially end up in rocky planets. So this would be a star that is a good candidate for hosting small planets. And from other studies that we have done since that original one, we're kind of coming up to this fraction of stars which show this perfect solar chemical mixture. It's about 15%. Now, if that is the case, then comes up a little bit of a problem also, which is that would mean that only 15% of stars like the sun host rocky planets or form rocky planets. However, Kepler is already telling us that this number is much larger than that. So now I wrote here, it's not necessarily the case, and that's where the details come in, because there's a number of problems with this. And let's start with the big one, this guy. Right. So if we look at the solar system, the planetary population of the solar system is Jupiter and everything else. Right? Jupiter dominates the solar system. So why are we saying that this is a signature of these little tiny things that are floating around in the solar system when we have a planet that clearly dominates the solar system? Why is that not a signature of Jupiter instead? Right, so Jupiter is 300 times more massive than Earth. So this is a problem we need to address first. We identified that problem early on, and we went out and looked at this system to try to address that problem. This is a binary system, 16 Cygni. It's two stars similar to the sun, but more importantly, very similar to each other. So they're twins of each other. And we can do a comparison of the two. we don't need to observe the sun even to make this comparison of the two. If we're only interested in seeing if there is a chemical composition difference between the two of them. More importantly, the secondary star has a planet. It's a gas giant, so that's the radial velocity variation over many decades. This is a work that started at McDonald Observatory and continues to this day. And the secondary shows this very clear radial velocity variation. So that's due to a planet with a mass of 1.5 Jupiter masses, minimum mass, of course. And the other one doesn't show any variation. So A doesn't have the same type of planet that B has, for sure. It could have little ones, of course, but it doesn't have a gas giant, for sure. So what we found for this system, we compared the composition of the two. This is A minus B. There's no sun anymore here. There's no solar comparison. This is just comparing primary minus secondary. So a binary, of course, the assumption is that they were born together at the same time. They should have the same composition, but if they don't, then something happened. Right? So identical composition would be here at 0. And each dot here, of course, is one chemical element, so there's clearly an offset here. They don't have the same composition. And also notice this is condensation temperature. They don't have the same composition, and this difference doesn't correlate with condensation temperature. It's just an offset. Everything just goes up. In this case, when we compare A to B. Right? So what this means is that B, the star that has a planet, is metal poor relative to the one that didn't form a planet. So this also can be explained by saying that the metals which are missing from the planet host star are in the planet. They were left behind in the planet. And the reason we don't see a correlation with condensation temperature is because this is a gas giant. A gas giant which has a core which is rocky, refractory rich, but it's also surrounded by this massive volatile rich envelope. So the two of them kind of compensate so that you just get an offset of the two. Yes.
Then earlier when you do the solar one, I saw that you have those lines for the 4 rocky planet, but do you also see the offsets due to the Jupiter?
That would be hard to detect. We don't see it, just to say that, or it's actually not possible to see it, because this is a comparison of 2 stars when we have one that we assume that contains the original composition of this other one. Right? That's the reference. It's a perfect reference. But when we compare sun to solar twins, they're just lookalikes of the sun. We cannot make the assumption that those other stars were born with the exact same chemical composition as the sun. But we can rely on the abundance ratios as a reference. But we cannot say anything about the absolute abundances in that case. So binaries are very important in this context. So, so to answer your question, it is not possible.
But then another question is, they can calculate for the rocky planet there is a trend,
Right.
a correlation with the condensing temperature. Is that also in the theory that it's flat for the gas giant?
There is, as far as I know, not being an expert on planet interiors, there is still a debate about how big the core is of giant planets. So depending on how big that is, that might have an impact on what the difference between volatiles and refractories is. But it's certainly less than in the case of rocky planets, which are essentially, in which the volatiles don't matter that much.
In other words, the chemical composition of Jupiter is much closer to that of the sun.
Yes, the mixture of metals, right? Other than hydrogen and helium, because we know that the metallicity of Jupiter is about 10% of the solar. But the mixture of metals, so things like carbon to nickel or something like that, that's solar, roughly solar. Yes.
What's the separation between these two binary partners?
I do not remember the number, but it's big. It's way
So it's
bigger.
larger than the possibilities that this that the approach planetary just took that out, and both should have theoretically the same regardless, the same composition regardless.
Yeah, I mean, they're separated enough that they have evolved essentially as single stars.
Okay.
And most of the binaries that we work on are that kind of binaries, because yeah, we know that there's issues with planet formation in closed binaries.
So to put it another way, the metals and the hydrogen helium are not, they came from different sources in the gas giant. Because if you just take off a Jupiter part of the sun and put it out, you're not going to change the abundance of anything. So if you're going to pull the metals off the star and put it somewhere, you can't pull hydrogen and helium off of the star came from.
Well, but you produce an offset like this, because
No,
this is
If you
H.
No, but if you pull a chunk of gas off of the star, you don't change its metals. And so that means the hydrogen and helium in the gas giant can't have come from the star. It can't have come from where the metals came.
So I guess what's happening is that the giant is retaining only the elements that are going to end up in the planet, and then the hydrogen and helium are going to end up in the sun. Not all of it, but more than whatever ends up in the planet. Okay, so as a summary, here I have this. The observations are suggesting then that when gas giant planet forms, you get an offset, no correlation with condensation temperature. When you form rocky planets, you get the trend. And maybe if you have a solar system analog, then you will get an offset, and then on top of that, a trend. However, that's very difficult to see unless you work with more binaries. But another issue with this is that if you notice how much the composition changes for a gas giant planet formation and a rocky planet formation, it's very similar. In fact, it's larger in the case of the most refractory elements. Even though, again, the rocky planets are very small, very low mass. So why are the signatures of this large size, large mass planets of similar amplitude, or maybe even smaller than the signatures of the little planets? That's another problem that we have to address. And what we think is the reason for that is, once again, that the planets and the star are forming at the same time. The star is not yet done. So this plot here shows the convective envelope mass of a solar type star, a function of h since zero, since it begins as a star. So the star begins fully convective, and as the core heats up, that envelope starts to shrink until it gets its final mass of about 2% at about 30 million years or so. Planets form in this region over here when the convective envelope is still very massive. And giant planets like Jupiter form first. They have to form very quick because they have to accumulate a large amount of gas. So what could be happening is that planets like Jupiter are forming earlier when the convective envelope mass is larger than that at the time that rocky planets form. And this is important because what we're seeing essentially is the star being stripped from metals by these planets. But when that happens also matters, right? Because when the gas that is being depleted by certain metals mixes with this large mass, then that's going to be diluted more than when it happens over here. So the effect is going to be more important if the convective envelope of the star is thinner, it's less massive, because there's less dilution. But that doesn't solve all the problems, because if we look at things like the disk fractions in young stellar associations, we see very young systems. In very young systems, most of the stars have disks, but then in systems with 10 million years of age or so, the disks are almost gone. So this kind of plot here is shown as evidence that planet formation happens very quickly. It happens on a time scale of a few million years. So if that's true, then a few million years is over here. We shouldn't even be seeing anything, because the mass of the convective envelopes of stars at that time is extremely massive. Massive enough to dilute any of these signatures that I've been talking to you about for the last almost 1 hour. So that is another problem, which, however, might have a solution in some recent developments in the field of star formation. Those models that I showed you a second ago are models in which a star forms just by a uniform collapse, right? The accretion rate is constant throughout the formation of the star, but there are observations and theory which suggest that stars don't form that way, that there are actually bursts of accretion that lead to this phenomenon of episodic accretion. And so in models of star formation with episodic accretion, not a uniform collapse, but a collapse with bursts of high accretion rate, you can have, this is the central temperature of the star as a function of age, for 4 different models of episodic accretion. Each one of these has a different history of episodic accretion in terms of how many bursts you get and what's the intensity of the bursts and so on. And there are some cases, like this blue model over here, in which the central temperature of the star goes up very quickly. So therefore the radiated zone also forms very quickly, and you end up with a convective envelope that is thin in 5 million years or so. Here's the evolution of the radiated zone, so the rest here, that's the convective envelope. So you reach the very thin convective envelope in about 5 million years. So this would kind of solve this problem that we have with the time scales, because you can have a situation in which you form a thin convective envelope by the time that this planet formed. And also, that might explain why we only see that 15% of the stars, solar-type stars, show the signature. Because this signature might be regulated by the episodic accretion history, meaning that there's only a fraction of the stars which have episodic accretion history that hits the core very quickly, whereas most of them actually do other things like this that take a longer time and therefore dilute the signatures more efficiently. So this could be, this has to be part of the story. First of all, in order to imprint the signature at all, we need this kind of ingredient. In addition to that, that could explain naturally this fraction. Naturally, if that's what the episodic accretion scenarios are actually predicting, which we don't know yet, because this is a relatively new thing. So this is, once again, similar explanation showing the observations at the top that support these ideas, right? When we compare the sun to the solar twins, we see a deficiency of refractories in the sun. This is condensation temperature. And in binaries like 16 Cygni, we see an offset. And in fact, there's a study we published earlier last year, in which we actually detected a tiny, tiny decrease in the refractories, which we think that is actually the signature of the core. So that there might be an offset, and on top of that, a tiny break there with condensation temperature, but mostly is an offset. And what happens when you have a uniform accretion star-forming model is that you need, in order to explain these amplitudes and those trends, you need Jupiter to form right over here, which is too late, and then Earth or other rocky planets even later than that, which is even more problematic. But with episodic accretion, you can solve those issues. In particular, if you take the models with few intense bursts as your representative of the solar case. So there is a lot of work in preparation, or things that we're working on. We're working on other binaries. We're working on a star in the Kepler field. So I'm going to quickly tell you about this. This is another binary, just like 16 Cygni, in which the secondary has a gas giant and the primary doesn't. Right. It's just like 16 Cygni, yet the difference is 0. The binary, actually, the two stars have the exact same composition. So you might think, if I didn't tell you the story about episodic accretion and all that, that would be a contradiction to the hypothesis, because this is completely different to the 16 Cygni scenario. But this could just be a situation in which the star had an episodic accretion history that was unfavorable to the imprint of the signature. So it happened too late. Now we have over here Kepler. Kepler field has a few solar analogs, and we took one of them. compared to a bunch of its twins. This was a particularly difficult problem. This is Kepler-10, the first rocky planet identified by the mission. And so what we expected is that it's also refractory poor, and in fact it is. But it was really difficult to prove that because finding twins of this Kepler target was hard, because the Kepler target is not a solar twin, it's not even a solar analog, it's a thick disk star. Finding a good sample of thick disk stars is difficult in the solar nebula, especially if you have to center them around a particular set of parameters. But anyway, we proved that again, that's refractory poor. The Kepler-10 is refractory poor, so that would be consistent with the hypothesis. This situation here is very complicated. XO2 shows a very nice difference between the north and south components. Right? This difference, there is an offset, it's small, but it's significant between the two stars. And then on top of that, there is a trend with condensation temperature. So this is a mix of the two effects that we have seen for the first time in a binary. We're seeing it. The problem with this is that XO2 not only has planets around both stars, but each star actually has a planet system. Right? XO2N has 2 planets identified, XO2S has 1 identified for sure, and 1 that might be or might not be a planet. So it's a very complicated situation. We don't have a simple story to tell as in the other cases, because it's, the masses for most of those planets are just lower limits. There's only 1 planet which is transiting, so that's the only one that we know for sure, but the other ones we don't. And then the most puzzling one is this one over here, in which the secondary has a planet, the primary doesn't, and here the primary is the metal poor one. So this one is completely inconsistent with this hypothesis, but it just complicates the picture even more, because I mean you can come up with the scenarios. Maybe that one had a planet and it just left, or it was eaten or something like that. So you can come up with different interpretations, because at this level there are many things that can affect the compositions of the stars. So the point I'm trying to make with this is that we haven't stopped right there with these 2 experiments, so the Sun and the 16 Cygni. We're looking at other systems to try to gather more information, and what it's becoming very clear, which should have been obvious at the beginning, is that the process is complicated. This whole process of planet formation and how it affects the star, it is intrinsically complicated, so we shouldn't expect it to have a really straightforward, simple correlation between observation and interpretation. It has to be studied on a more statistical sense. We need larger samples and start to study different scenarios. We also need to know a little more about how stars form, how this episodic accretion is affecting not just the evolution of the convective envelope of the star, but also how is it affecting the planet formation itself. So we don't really know any of those details. So in conclusion, I'm going to say this is very solid. This chemical anomalies that we have seen, that the Sun is deficient in refractories, there's no doubt about that. There's no doubt also that binaries, some binaries at least, show chemical differences, even though we might expect them to have the same composition. So this is very solid. We need an explanation for this. Now we have an idea, which is that this is due to planet formation. It's in all fairness, it's a debatable connection that we're making, but don't forget that these things are real. We need to explain it somehow. And I think I'll stop there. Thank you.
So are you limited right now by the volume you can survey, or by this telescope line, in terms of the number of twins that you can do this type of detailed analysis?
I would say volume more than telescope time, because even though it requires more time than usual, of course, it is not, and the stars are still bright enough for us, except Kepler field. Right? So when we try to do Kepler field, the problem is the brightest solar type stars in the Kepler field are going to be 12 magnitude. I mean, there might be a few that are brighter than that, but the bulk of them are going to be 12 magnitude. 13 magnitude, and then finding a sample of twins of that is also difficult, because Kepler field is far away, and And also there's that other assumption too that, you know, when we work locally, we're kind of under the assumption that the mixture of stars in the solar neighborhood is still similar enough, or perhaps more similar enough to each other than this Kepler field, which is kind of far. It's not solar neighborhood anymore, so it's a little bit dangerous to go beyond that.
Any other questions?
So in that sense, will TESS be a better mission for you?
Yes. If they give us brighter, closer stars that we can work with, yes. But also, so I've been talking mostly about solar twins, but we have done the experiment of working with just twins, like stars which are twins of each other. And we did this experiment with F-type dwarfs and then with metal-rich, a little bit cooler than the sun stars. So we don't need solar twins exclusively, right? As long as we can build a sample of the stars which are all twins of each other, we have demonstrated that we can get this kind of error bar, the 0.01 Bex error bar. So, yeah.
So are you going to check these results by using near infrared spectrum to see if you get the same errors in temperature and gravity and the same trends?
In the near infrared,
Now the near infrared spectrum.
right. I'm not very familiar with that region, so I wouldn't know if there is enough features to do this kind of work, at least not to the extent that we have in the optical.
But you can check the stellar parameters using the iron.
Right.
Well, I think that would be a very important test because you've got completely different continuous opacity.
Okay.
Test to see whether you're actually getting these really precise
Right.
stellar parameters.
Right. We're also testing other species or other elements for which we have both species, neutral and ionized, titanium and nickel, or not, titanium and chromium. In the optical, they both have both neutral and ionized, and they're certainly probing different layers of the stellar atmospheres. And what we're finding is when some of these points are chromium 1 and chromium 2, or titanium 1 and titanium 2, and they always agree. So at least at that very basic level, we're okay, but we should definitely try deriving parameters, for example, not using iron, but using titanium. It's a good test. Yeah.
So for the twins, not the solar twins, but for the twins in the binary system defined, those you also to limit the difference of the temperature of the two stars are less than 100.
Yeah.
I'm just wondering if you change from like 100 to 300, you can make like much larger sample, a large temperature. Will that make a difference in the temperature difference, make a big error that we can't use those sampling for? Or?
I would think so. Yeah, I would think so because we have tried. In fact, in one of my papers I had a sample of 60 solar analogs, and then out of those 60, only 20 were solar twins by our definition. Right? The trend gets so fuzzy when we use all 60 that we really need to concentrate on those 20, which are within the limit of high precision.
Any other questions? Okay. So I scheduled grad student cross